Yeah, thank you and welcome to this talk. It's an experience report, and I have to report the following experience. Formal verification of real-world Haskell code is possible, but verification is futile because Haskell code has no bugs. Okay. But in order to get that experience, we have to formally verify Haskell code. And how do you do that? Well, obviously, you can't, because Haskell has no formal semantics. But if you really want to, then you have to be a bit pragmatic. And you can maybe observe that there are other functional languages like coq that do have a formal semantics and moreover have a very rich machinery of doing verification. So if I want to verify Haskell code, maybe I can just assume the Haskell code is coq code. Unfortunately, they differ in aspects like the number of colons used for type signatures. And to fix that, or to work around that, we have created a tool, very creatively called hs-to-coq, that translates Haskell to coq and allows us then to verify Haskell code by pretending it's coq code. And you might have some qualms about the validity of this, so let me just pull out the hammer that's called fast and loose reasoning is morally correct, and ignore all the other concerns for now. So I said real-world Haskell code. In the paper about hs-to-coq half a year ago, we were looking at textbook level of examples of Haskell, and it worked very well there. But that's not real-world Haskell code. With real-world code, I mean code that is actually being used out there, that has been around for decades, that has been optimized for performance, and maybe most importantly, has not been written with verification in mind. And one example of such code is the Haskell containers library. It provides commonly important data structures, and we are focusing on the set modules. So there's data set. It's a weight-balanced binary search tree for elements of a type that is linearly ordered. And there's inset, which is a big endian Patricia tree, which means you're branching on the bits of numbers. And I consider this real-world Haskell code because it stems from the last millennium. It's the third most popular library on Hackage after base and byte string. And there are whole research papers devoted to squeezing out a few more % of performance. And it's doing that partly by using obscure feature of GHG like really unsafe pointer equality. So we wanted to verify this library. Now, saying that we're verifying a library doesn't mean anything until I tell you what we proved about them. So what are the theorems? What is the specification? And we embarked on a journey to find specifications. And the first one that we found, most obviously, are the invariants of the data type. And you can find them, invariants of the data type, and you can find them in comments in the source code. Obviously, binary search trees needs to have a certain form to be well-formed. And the correctness of all operations depend on these invariants. So it's very crucial to verify that. But it's also boring, because the term data type invariant is just a euphemism for insufficiently powerful type system. So maybe in 10 years, we can use liquid Haskell or defended Haskell and don't have to deal with that anymore. This decade, we still have to. So we did the thing you would expect, inductive predicate, describing the invariants and then proving that all operations preserve them. Another source of specification that we found in the source code are the quick check properties in the test suite. So containers uses quick check, so there are functions like this one that take sets and test whether some property of the operation holds, and the quick check library feeds it with lots of random inputs, and you can find bugs this way. But you don't have to squint a lot to see that this looks like a theorem, and it's a theorem that we might want to prove. Moreover, because we are now working in coq, and in coq, propositions are types, and types are just terms, and we have a tool that translates Haskell terms to coq terms. We now also have a tool that translates quick check properties to coq propositions. And we can automatically translate this to a proposition, which we then can manually prove in a theorem, which I find a very neat application of the translator. Another smaller but also interesting source of theorems to prove are rewrite rules. These are defined in the library, and they instruct the compiler to modify the user's code in a certain way. And they are completely unchecked. which means that they can wreak arbitrary havoc in the user's code. So obviously, there's a strong motivation to prove that these actually do preserve the meaning of the user's code, and luckily they do. And then yet another source of interesting theorems to prove are type classes. Now, a type class is more than just a list of type signatures. A type class has a meaning, has an intuition behind it, and if you're lucky, you can find this meaning written down as equations, as laws, in the documentation of the type class, such in this case, which is the documentation of the monoid type class. So in Haskell, you can find these specifications only in documentation or in folklore. In coq, we can do better, and we can actually define a type class that also includes these laws as proof obligations. And by instantiating this type class with the data types that we get out of the containers library, we can verify that the instances in the containers library, e, quad, and monoid, actually are lawful and make sense as type class instances. So these four sources of specifications all stem directly out of the containers library. So in a way, they're self-referential. They're a bit of navel-gazing. So we're looking for external specifications to make sure that this really is a set data type and not a set card game. And we found that because we're in the setting of coq, we can use the coq standard library, which provides a module, the fset interface, which defines what it means for a data type to be a set. So it lists the operations, and more importantly, it also lists properties of these operations that make this what you would expect from a type, from a set type. And we were able to instantiate this module with the implementation from the containers library after translation, giving us good assurance that when you load data.set, you really get a set data type. So there's plenty to prove. But before we can prove it, we have to get the code into coq. And for simple cases, like the ln function, as I said, this is a completely automatic process using hs-to-coq, and you get something out of it that is actually usable and interesting. But even in this very simple example, you will find that we might want to wish to tweak the output. Note that bool is capitalized here, which means this is the coq translation of Haskell's bool data type, which is fine, but there already is a bool data type in coq. It's lowercase bool, and maybe we want to use that in our translation to connect to existing libraries. Now, we could just start editing the output of the translation, but that would be very unsatisfactory, because then when we change the code or something else, and we run the tool again, we lose all our edits, obviously. So a principle in our work here was to not modify either the input or the output. Instead, we can provide hs-to-coq with a so-called edit file, with a plain text file that instructs it to change something in its translation process. For example, we can tell it, these types and functions from Haskell world, map them to the existing types and functions in the coq world. And this is not only very useful for maintenance, but it's maybe even more useful as a declarative list of all the leaps of faith that we took, all the assumptions we had to make. Because here we're just postulating that bool and coq behaves like bool and Haskell, but we're not proving it. So somebody who wants to check our verification, or maybe we want to check it ourselves, can go through these edit files and very concisely see all the kinds of steps we had to take there. So as we scale from toy examples to real-world code, there are a few challenges that we have to overcome in this translation, and I will show you 3 of them. There are more in the extended version of the paper. And the first one is partiality. You don't have to read that code. The slogan of our CPP paper was, total Haskell is reasonable coq. And it's reasonable to assume that if we are mapping something into a logic of total functions like coq, that we can only reason about total code. But reality required us to reconsider, because there is partiality in the containers library. This is a very crucial function that does some rebalancing, and the second line from the bottom calls error. Now, this code path should not be reachable under normal execution, so if the input is well formed. But still, we have to translate it to coq to do something. So what can we do with this error function? Now, we can't have a function of this type in coq. It will completely break the soundness of the system. So we took inspiration from what the Isabelle people do. In Isabelle, you can have a function of this type, and it does not break soundness. Why is that? Because Isabelle is a logic where all types are inhabited. And if all types are inhabited, this function does not break anything. So we model this in coq by introducing a type class for inhabited functions, inhabited types, and we constrain the error function using this type class. And then we add lots of instances for common types. And now we can translate all occurrences of error at these types and make progress. Can we still prove that balance R never calls error? Which would be an interesting thing to know, wouldn't it? In a strict sense, no. Because error now is just a value of the type, and it's indistinguishable from the value that it is at this type. But we can do some trick to almost get there. We can make this definition in coq opaque, which means that during the verification, during proofs, coq will not look at the definition. And that means if we can actually conclude the proof, something about balance R, we know that the actual value of error did not matter. And for all purposes, practical and pragmatic, that means that error was not used in any relevant execution of the code. From questions of paternity, it's really close to questions of termination. And we've seen in the example of LM that we can translate obviously structurally recursive functions to coq and use the coq's built-in fix operator, and things are fine. But not all code is like this. There's code, and again, you don't have to read the details here, in the containers library that is only terminating on certain inputs. And where the termination argument is intricate, requires lemma about other things, maybe even defined in the same function, that makes it really unpleasant to craft the termination argument ahead of time before that we can define the function and pass it as a tactic. So again, we had to, again, we took some inspiration from Isabelle. We define an axiom that we call deferred fix. And it can plug it in and write for the fix operator of coq. And it just sits there and doesn't do anything on its own. It just holds your code. And then we have this somewhat scary looking axiom, which says nothing else but during the verification, when you want to unfold the fix point once, then you have to prove that the function extensionally only recurses on smaller arguments according to a well-founded order, which is what I understand is termination in some sense. And we can add this axiom to our theory without losing too much sleep over it, because we can actually prove this as a lemma if we enable classical logic and axiom of choice in coq. So it's a choice to do this, but it allows us to make more progress, and for practical purposes, this is definitely worth it. And then maybe the last challenge that I want to report to is, I already alluded at the beginning, this really unsafe point equality function that GHG provides. It's a function that takes two arguments, you pass it two arguments. If it returns true, it means both arguments are represented by pointers to the same address in the heap. If it returns false, you don't know anything. And clearly, there's no pointer equality function in coq. It's a completely different world of abstraction there. So how can we make progress with code that uses unsafe pointer equality, which exists in the containers library? So a first approach would be to say, okay, we just define this in coq to always return false. This matches the specification, but it's unsatisfactory because it means that in the two branches of the code that checks some pointer equality, we only get to look at the case where it's false. The true case becomes dead code in coq, and we will not find any bugs in that part of the code. Again, we can improve the situation by making the thing opaque, which means that during proving, we don't know it's always false. So we have to look at the true case as well in our proofs, and it forces us to go on both ways. And then we also prove this lemma that says that if pointer equality returns true, not that it ever does in coq, but that doesn't matter, if it returns true, then we are allowed to assume that the arguments are structurally equal, which is a pretty good approximation of the idea of being represented by a pointer to the same address in the heap. And with this in place, we were able to verify the code in the containers that uses unsafe pointer quality and verify both code paths. Okay, so with these kind of tricks, we get the Haskell code into coq, and we have our theorems. So 15,000 lines of coq proofs later, we know that there are no bugs. We also found that the proofs are somewhat maintainable. So we survived an upgrade of the containers library to a new version, and it took us only an afternoon during PLDI to fix that. We thought that the theory of weight-balanced binary search trees was pretty much thoroughly done in literature, but we found that there's some theoretical questions on how to verify these things that we stumbled upon that were not answered in literature, mainly because the containers library uses a slightly different invariant than the literature, so there were some open questions that we could fix. And because we stared a lot at the code, we found that the union function on data set could be made a little bit faster. And that's now a patch that was merged, so if you're using the latest version of containers, you're already benefiting from this work, in a way. And overall, the experience was that, yes, formal verification of real-world Haskell code is possible. Encouraged by this result, maybe a little glimpse on ongoing work. So the people at Penn, in particular Antal, are now turning it up yet another notch, and they're trying to verify parts of GHD itself, which I would really, really consider real-world Haskell code. And actually, we already found a bug. So maybe the observation from the first slide that Haskell code has no bugs is not as universal as I was hope it would be. There's a project that formalizes RISC-V, the instruction set semantics in Haskell, and wants to have it in coq as well, so uses hs-to-coq. And then there's a project that uses Haskell to specify the semantics of RISC-V and wants to have it in coq, and they're using hs-to-coq, and they're completely separate projects. And finally, we started writing documentation. So you too can now use hs-to-coq for all your verification needs of Haskell. Thank you.
Plenty of questions. Did you try verifying an old buggy version of the containers library?
Oh, interesting idea. Trying to remember. I thought there was some bug that we looked at in the history, that we found in the history. But the containers code is just so bug-free. It's horrifying. It's. I think there was one bug in some of the inset modules, and it was only there because the quick check properties were written but not added to the test suite, like not added to a list of tests. And basically, I guess I should include this in my conclusion, the bug freeness of containers is, I think, mostly because of quick check is just a great tool to get bugs out of it. We didn't try to verify it because we looked at the bug and we saw immediately that we would have found it.
So precisely related to quick check, did you find any invariants in comments that were not tested by quick check properties?
What we did find was that for the inset module, the test suite had a function that was testing whether all the invariants hold. But this function was not properly recursing into all the leaves, so it was not complete. And we also tried to, so we found this code, both for set and inset, and we wanted to verify that when our invariant holds, then this function returns true and the other way around, and we noticed we couldn't. So we found bugs in the test suite, and we fixed them or helped them fix that.
So you bridge the gap between Haskell and the coq semantics with nice tricks like the error story. So did you cover it all? Would there be programs that you could prove correct with coq but don't behave as expected in Haskell?
Is the question, so are there programs that we could prove? So this is a very pragmatic approach, and I think if a malicious user could easily fool the system and do something that it would break. I think maybe the not so malicious case would be partiality. Because we do these tricks where the error becomes this value of a type, means that if you evaluate some exception throwing term, but then don't use the result, like pass it to seq as EQ, not the guy in critical types, then you would crash in Haskell, but there's no way of seeing that in coq. So maybe that's an example.
Okay, so technical question last. Can you explain how you define pointer ec to enable proving pointer ec that you had in your slide?
Sorry, say that again.
I guess if you come back to the slide where you define the, this one.
Okay.
Yeah. So the question is, can you explain how you define pointer ec?
Oh, so to prove this? Well, I define pointer ec like this. It's always false. So this lemma is easily provable.
Okay.
And by hiding the fact that it's false, I force myself to go down a branch in coq that if you think of coq as something that executes, will never happen. But we don't care about how coq executes, we care about how our proofs about the coq code reflect about the Haskell code. And in Haskell, it may return true, and that makes sense somehow.
Somehow, okay. Well, thank you, Joachim.
Okay, thank you.
That's the end of the session.